So a pebble is dropped in a calm pond, causing ripples in the shape of concentric circles. So these concentric circles, they're just saying circles that are kind of outside of each other. Okay? So the radius of the outer ripple is increasing at a constant rate of 1 foot per second. Here we go. I gotta start you off immediately with the acronym. Now, I'm not even kidding. Because of the fact that this was such a dreadful unit, I'm not even kidding. We developed this like the very first year that I taught calc, and it helped a lot of students. There's your acronym. This is the acronym because it's such a dreadful unit. DREADS is the acronym that I think you should use. That will at least get your brain going as far as what are the steps that I could start off at and where I should be looking and when I should be asking myself these questions. Because a lot is going on. And this is as close to a template that I could come up with. Number one, draw the diagram. If you see it, it's so much easier to start setting things up. And you don't have to go crazy and elaborate. Just draw the diagram. Number two, rates that are given and the ones that we need to find. This is so important to get started off. What do you think E stands for? The equation. What equation are you working with? Are you talking about the equation of a circumference of a circle? Are you talking about the equation for the surface area of a triangular prism? What are you talking about? So the equation relates, otherwise related rates, it relates all the pieces together that you're trying to look at one specific point in time. What do you think the second one, or this D, represents? The derivative. This is the derivative, yeah. The differentiation of this equation. So the derivative of this guy. You with me? And guys, if you want to, please put it in your notes. Most likely it's going to be in implicit form. Okay? And then the last one, the last two are substitute the given information and solve for the unknown. If you do this, I guarantee you, you have a fighting chance. Like 90%, you're almost guaranteed that you will be able to do this. If you know the calculus steps, you'll be able to solve this problem.
You said the derivative will pretty much always be implicit.
Implicit, yeah.
Like in the example you gave us, there was the y on one side that wasn't obviously an implicit equation. When would it not?
It will. Just go for implicit. And here's the thing. I like his question and the timing because it makes me clarify it just a little bit better. The more thing that I want you to gravitate to, it's going to be in respect to time. So all these small little variables are going to be in respect to time that you're deriving. Okay? And if it's explicitly given to you, that's okay as well. It could be both. But what I needed to clarify is it's in respect to time. Questions? Yeah?
So is it only explicit when time on that side by itself?
Or when any variables on the. But the thing is, we're going to have multiple variables. You'll see what I'm talking about when we get there, okay? All right. Diagram, done. The rates that are given. Well, this sentence right here gave us a rate. And the reason why I know it gave us a rate is because it said it right there. That important word will tell you you were just given something dt just now. Okay? So d something dt is equal to 1 feet per second. Now, can you tell me, the 1, the way it's given, it's positive. What's happening with these circles? They're growing. If it was a negative 1, what would be happening with the circles? They'd be decreasing. That's huge. You got to get that in your brain right now. If the rate of change is positive, then the function is increasing. Again, if f prime is positive, f of x is increasing. But if f prime is negative, f of x is decreasing. Okay? All right. So what variable should we give this? r, the radius, okay? So when the radius is 4 feet, oops, we'll say when r equals 4 feet, we want to know, find the rate, so here we go, find the rate at which the area of the water is disturbed. What variable should I use? A. And I'm going to use capital letters for area and volume. You with me? For area and volume, we use capital letters. So A for area, B for volume. We do not know this, but we want to find it. Now, the rates that are given in the and are unknown, check, done. Now we got to go back to geometry, and hopefully your geometry teacher forced you in a lot of ways to memorize all these equations that you're going to have to be very, very familiar with right now. Here we go. What is the equation pi r squared? Here we go. So the area is pi r squared. This is the equation that we're working with because we're not talking about circumference. We're talking about area of a circle. Now, this line is so important. This will make or break you as far as those of you who understand these two questions that you should ask yourself right here and right now. This will be very easy for you or will remain difficult for you. Okay, here we go. The two questions are this. Question number 1 is the variable changing or is the variable constant? Is the variable that you're looking at changing or constant? If it's changing, leave it as a variable. If it's constant, plug in that value immediately. Let me write that down. If it's changing, you're going to leave as the variable. If it's constant, we're going to substitute or plug in that value for the constant immediately because of constant multiple rule. You with me? Number 2 is, should we leave it as that variable? 2 is the harder one, okay? Should we leave it as the variable or replace it with a different variable? We say in terms of what variable? Should we change, and that's a question that you're asking, to a different variable, the one that we're given? Okay, let me talk to these questions with you right now. Okay, here we go. What did I say A stood for? Area. Is the area changing if this was an active motion? Yes. So because it's changing, I'm going to leave it as A. Okay? The second question is, should we write it in terms of a different variable? Should I change A to something else, or should I leave it as A? I'm going to leave it as A because how else will I ever get this piece when I derive it? If I change it to a different letter, I will never be able to get dA dt. Okay, so that's question number 2. Go with me? Now let's check. We have to check all the variables with these same 2 questions. Does R change? Yes. So I'm going to leave it as what? R. Should I change R to something else? No, because how else will I ever be able to get a dr dt if I change it to a different letter when I derive these? Questions? All right. Why did I not highlight pi? Because it's a constant. Okay, here we go. So this step is done. Now we're going to differentiate right here, right now, in respect to t. What's the derivative of the left? dA dt. Careful, remember you said it, pi is a constant. So to me, I wouldn't even look at pi. I would just concentrate on r squared. And what's the derivative of r squared in respect to t? Yes, 2r dr dt. And now, yep, someone was about to say it, constant multiple rule back that pi into it. Okay? Now here we go. I'm going to use a positive 1 for dr dt. Remember, I'm looking for dA dt. That's my unknown. I'm looking for this. That means I should have an r somewhere. If not, I should be able to find an r. Because sometimes you're not just going to be given that r. You have to find it. What is r? 4. Oops, not there. So this will become pi times 2 times 4 times a positive 1 and dA dt. Guys, if you ever have something in pi, unless I give you a calculator, which I finally will give you a calculator for this test, there's some calculator pieces that you need the calculator for. If it's a non-calculator, just leave it in terms of pi. So the answer is 8 pi. Now, let's think about this. dA dt is 8 pi. Now, we got to think about our units. It's in respect to time, so we know it's going to be like feet per second or something like that. But because it's an area, because it's an area, you already said it, it's not going to just be a rectilinear foot. It will be a two-dimensional cross-section of feet squared. So this will be a feet, square feet, we'll say per second. Let's default to feet per second, okay? Unless it says, it did say. All right, feet squared per second. Let me tell you the difference. If it was volume, what would I have? Feet cubed per second. What if it was still area, but it was acceleration? It'd be feet squared per second squared. If it was volume and it was acceleration, it would be feet cubed per second squared. All right, good. Any questions before I move on to the first? Because that's just the first one. On a scale from 1 to 10, this is probably like a 2. Yes?
What if the rate at which it's increasing isn't constant?
If it's not constant, then you can't do that. Listen, did you hear what he said? He goes, what if the rate that it's increasing isn't constant? Then that's multivariable. That's more. That's like Calc 3. You won't experience any of that. Not this year. Okay? Here we go. Real quick, because I like Wilson's question. Real quick. The radius was increasing at a constant rate of 1 foot per second. That means dr dt is 1. What's the acceleration of dr dt? 0, because the derivative of this derivative, what's the derivative of a constant, which is what he was referring to? 0. That's important. Those are the level 7 to 9 problems he's already going to, that you'll have, that you're going to have to think about all these different things. Okay? All right, here we go. Water runs out of a conical tank. So real quick, let's come over here. This is two-dimensional velocity. Okay? And this is probably like a level 2.